Today, we're going to pull back the curtain on the powerful systems that wrangle the modern world's absolute explosion of data. I mean, these are the invisible engines of the cloud, making sense of information on a scale that not too long ago was pure science fiction. Let's jump in.
So, to really wrap our heads around the scale we're dealing with, let's start with this number, 1 petabyte. What is that? It's 1,000,000 gigabytes. If you stored that as MP3s, you'd have more than 2,000 years of non-stop music. It's just a colossal amount of information, but for the modern internet, it's pretty much just another day at the office.
Now, to see that number in the wild, let's rewind to 2010. You remember games like Farmville, right? Well, at their peak, the company behind them, Zynga, was moving 1 petabyte of data every single day. They were reportedly adding 1,000 new servers a week just to keep up. Insane. But believe it or not, even that is just a drop in the bucket. Around that same time, Google was processing something like 24 petabytes of information daily. That's a complete avalanche of search queries, log files, emails, pretty much everything that flows through their entire ecosystem. And that, right there, leads us to the big question. How on earth can any system possibly manage that much data? This is the core challenge of what we call big data. Data sets so ridiculously massive they just completely break traditional tools like databases or even a simple spreadsheet.
So, to really get why the new solutions are so brilliant, we first have to understand why the old methods failed so spectacularly. This wasn't just about needing a bigger hard drive, the whole architecture was fundamentally broken for this new scale.
Okay, so think about it like this. The old school approach was all about one single, incredibly powerful, and very, very expensive server. It ran a structured database, kind of like a perfectly organized spreadsheet. But big data, it's messy, it's unstructured, and it arrives way too fast. So the new approach just throws that idea out. Instead, it uses an army of thousands of cheap, commodity computers. We're talking standard, off-the-shelf machines. And that shift had huge economic implications. Instead of one multi-million-dollar machine, companies could buy thousands of way cheaper servers, suddenly making massive scale actually affordable.
You know, what's really wild is that the biggest bottleneck, the thing that slowed everything down, wasn't always the processing power. It was just moving the data. When you have petabytes of stuff stored somewhere, simply getting that data over to the processor for analysis becomes this monumental task that can grind everything to a halt.
And this right here led to an absolutely paradigm-shifting idea, a total game changer. If moving the mountain of data is the problem, well then don't. Instead, you move your small analysis programs, your computation, out to the thousands of machines where the data already lives. It's such a simple concept, but with truly profound implications.
So the first piece of this puzzle was that we needed a completely new way to store all this data, something designed from the ground up for this brand new, distributed world.
And that's where the distributed file system comes in. Instead of one huge, expensive storage box, systems like the Google File System, or GFS, chop up big files into smaller chunks and scatter them across thousands of those inexpensive computers. And here's the really clever part. It makes multiple copies of everything. So if one machine dies, poof, the data's still safe, and the system doesn't even blink.
This slide just illustrates the idea perfectly. It uses Google's Bigtable, which is a database built right on top of GFS. You've got a single master server that acts like a traffic cop. It doesn't hold the data itself, but it keeps a master list of exactly which tablet server is holding which piece, or tablet, of the data. It's a really smart way to keep things organized while letting the whole system scale out massively.
Okay, so we've spread our data across thousands of machines. Fantastic. But now what? How do you actually get all of them to work together to answer a single question like, how many people visited my website yesterday? This is where the real hero of our story, MapReduce, enters the scene. Now, it's not a single piece of software. Think of it more like a recipe, a programming model for breaking a massive computational problem into tiny, independent pieces that can all be run at the same time across that whole army of computers. And that recipe has two incredibly simple core steps. You have the map phase. That's where each individual computer analyzes its own little local chunk of data. Then you have the reduced phase, which takes all those little partial answers from the map phase and combines them or aggregates them into one final result. Analyze, then aggregate. Let's make this real with our website visit example. You'd have thousands of map tasks running at the same time, each one just looking at a tiny piece of the server log. For every single visit it finds, it just spits out a simple pair, the URL that was visited and the number 1. That's it.
Then a reduce task comes along, gathers up all the pairs for a specific URL, and just adds up all the ones. And the result? A perfect final count for each page.
And this slide just visualizes that whole workflow beautifully. You see the input data on the left gets split up and fed to all those parallel map tasks. Their output is then automatically shuffled and sorted by key. That's the real magic step in the middle, before it's all sent off to the reduce tasks, which give you your final answer.
So this is all some really elegant, cool technology, right? But what does it actually power? What's the real-world impact of all this? Well, the short answer is pretty much everything you do online.
I mean, these systems are the invisible engines that index the entire web for Google search. They power your social media feeds on Facebook and Twitter, and they analyze massive, massive data sets in scientific research, everything from medical records to particle physics experiments at the Large Hadron Collider.
At the end of the day, it's this elegant one-two punch, distributing the data across cheap computers and then distributing the computation to that data that turned the whole big data problem from this impossible obstacle into a massive opportunity for innovation.
And this really leaves us with a final, fascinating thought. We've built these incredible engines to make sense of the world as it is today. Now that we have this kind of power, what new questions are we going to ask? And what incredible discoveries will they unlock tomorrow?